All right, so again, today is March 26th, and we're going to be going over polars. Um, we're going to start by just talking about where these guys come from. Basically, they're sourced from vectors. Forget the fact that the graph looks like a circle for now. I want you to imagine that we have just an ordinary old vector. We've got ourselves an x component, and we've got ourselves a y component. And what's been happening with vectors is those x's are defined by a function with respect to time. The y's likewise are a function defined by respect to time. Each of those functions define the position of a particle. These functions, these vectors can each be derived with respect to time. So we get the velocity and then in turn the acceleration. Where we look at the combination of these two components is with something called the resultant. And it would be something like this. This is the resultant, and this is our angle theta. All right, so now maybe you're starting to see the reason for the circularity of this graph here. The essence of polars is instead of graphing with respect to x and y, what if we were to come up with a system that graphed with respect to, okay, let me back this up, a polar, its ordered pairs are the resultant, which is, let's call it the radius, and the angle theta. Instead of x's and y's, the polar coordinate system is r and theta. Now, a couple of ways to get yourself back home. These are essential relations in order to get between polar and Cartesian. When I say Cartesian, I'm talking the XY coordinate system. The first one is that the way you could get the y, and I teach my geometry kids this. Let's see, the sine of theta is equal to y over r, and that's the key for how we get y. Y is equal to r sine theta. So let me just write. You guys shouldn't need to see that. Here is the code for how you would transform from one to the other. Y equals r sine theta, and the x is equal to r cosine of theta. Another phenomenon that'll get you from one to the other is the Pythagorean theorem. X squared plus y squared is equal to r squared. And then finally, we've got that the tangent of theta is equal to y over x. And these four, they've got a little special box in your textbook. And I think it's even a shaded box, which means it's really important. These are your map of how you're going to get between Cartesian and polar, all right? When you're doing the ebook assignment, I would say a majority of the questions are just translating a polar equation to a Cartesian one and using these various codes of how you would get from one to the other. The other thing you're going to see in the ebook assignment is a bunch of graphs. Use your calculator. I mean, we're going to graph one manually, but I would suggest you use your calculator to see the picture. There's one type of graph that you can't do on your calculator. We'll talk about that next week. If you want a sneak peek, it's at the very end of, I think it's chapter 11, is the parametrics, vectors, and polars, and they call it a library of the polar equations, or a gallery of. And it's actually they're very, very cool pictures. So let's just get to doing one of them. Hopefully you have a little bit of a bearings on. Okay, as I'm looking at this is a polar-oriented graph. I'm not really sure why they insist on having the X and the Y there. That might just be a carryover from the software that I get with Grapher. But basically, the radius, the R, okay, here's R equals 1 is right there. R equals 2 is right there. R equals 3 is off the page. That's the R. The theta is this angle from here's theta equals And I'm going to work in 0 degrees for now. In calculus, all of your work is going to be, all of your integration and derivatives is going to be in radians. This is a preference. I just see things better in degrees. And notice that we go counterclockwise. There's 15 degrees, 30 degrees. We hit the y-axis at 90 degrees, and we make a full circle at 360 degrees. All right, so lose those. What I'd like to do is I'd like to graph the equation, and you can sort of see it. It's in the upper right-hand corner. I want to be graphing this guy right here, r equals sine theta. Okay, I just plugged in a bunch of values for reasonable values. You'll see the shape soon enough. In fact, you may have an inkling of what this thing is before we even graph it. But the way you graph this, I would hope that you would work along with me on this. Yeah, all of our work is going to be in the first and second quadrants. Please work along with me on this. The way in which you graph these is as follows. We start at, we take our direction of 0 degrees, and we're going to go an r of 0. So basically, we're starting at the origin, all right? At 30 degrees, well, we're going to follow, our direction is going to be towards this 30-degree mark here. And the sine of 30 degrees is 0.5. So we're going to go out to 0.5, which is right about there. Do you see it? There's 0.5. Okay, at 45 degrees, we're at about 0.71. So 45 degrees is right here. 0.71. I'm going to go to about, there's about 0.71, give or take. All right, at 60 degrees, we're hitting the 0.87 mark, which is ballpark here. And then at 90 degrees, we make it to 1. And hopefully you guys are starting to see the shape. If I start to connect this together, you see what's forming. And as we work our way down the side at 120 degrees, okay, follow 120. We are at 0.87, which is about there, more or less. At 135 degrees, follow this. This is your trajectory. We're going to go to 0.71, which ballpark is around there somewhere. At 150 degrees, follow this trajectory. We're 0.5, which is here. And then at 180 degrees, yes, we have completed our circle. Okay, so that is the graph of r sine theta. One of the curious things that you should be aware of is notice what happens if we go a second loop around. We've got 210 degrees. Well, at 210 degrees, I didn't graph it. It's, I believe this direction is 210 degrees. But notice that the r is a negative number. Let me switch color here. So we're heading in this direction, and it's a value of 0.5, but it's negative 0.5. So it actually takes us to right there. You see that? And then if we were to go at 225 degrees, that's down in this direction, and it's taking us, now notice it's negative 0.71. So 0.71 would be somewhere down here, but we're negative 0.71, which puts us back here. So although we've got different degrees and we've got different r values, the net effect is that by going 1 pi revolution, or by going 1 pi, we've created 1 revolution, and our second pi actually creates a second revolution. All right, so let's do a picture of this real quick. Get out of pen mode. There it is. There's r sine theta. There's the circle that we just graphed. All right. Let me show you how to graph this in a calculator. Get your if you have it, get your calculator out. Please make sure that you are in polar mode. So on your TI-84, that's going to be the 4th option down. We've used parametric and POL. That's our abbreviation for polar. Make sure you're in polar mode. And we do want to be in radians. Again, I think degrees is a little more user-friendly, but calculus demands radians. So we're set to go. And then you hop into your equation editor. And if we want to graph the sine of theta, we've got r equals, okay, we're going to hit sine. And notice when we hit the variable x and t, well, if you access the button that you would normally press for x's, since we're in radian mode now, or I'm sorry, since we're in polar mode, it automatically defaults to a theta for us. So this is the, yeah, so there's our graph. And if we want to graph it, let's make sure our windows are set. If I go from 0 to 2 pi, I'm going to end up making 2 laps of the circle. So let's just go to, how about we go to pi over 2, second pi divided by 2. My window, I'm going to set as negative 1.5, positive 1.5, and y min will be negative 1/2 and positive 1.5. And there you go. That's a pretty decent window right there. Let's finish off the second half of this circle by going, instead of going to pi over 2, why didn't I just do this from the beginning? Go to pi, and graph it, and there's our circle. All right. So that is probably the most basic. No, actually, there's a couple more basic polar equations. As far as relevant polar equations, this is the most basic relevant polar equation we can graph. The last thing I'd like to do with today is I'd like to do a derivative and an integral, and let's use this circle. For derivatives, the question that I'm going to be asking you guys is this. What is the tangent at pi over 6? All right, so we will work on that. Pi over 6 is 30 degrees here. So ballpark, we're looking at, this is the point, and we're looking at a tangent line. This is the tangent line. All right, so here's how we're going to go after this thing. This is going to look very familiar to you as far as our parametrics go. Our derivative, we're looking for a dy dx, and that's going to come from a dy d theta over a dx d theta. This is the exact format you've seen for parametrics. So what we've got to do is we've got to get the dy d theta. Well, remember that our equation was r equals the, what was it, sine of theta? So our y is, okay, don't forget the conversions that I gave you guys earlier. Y is equal to r sine theta, and x is equal to r cosine of theta. So for this particular equation, since r is the sine of thetas, for this particular circle, our y will be sine of theta, which is r, and you're always multiplying by sine of theta. So we get sine of theta times sine of theta. All right, our x is going to be, again, the r is sine of theta, and our you're always multiplying when you're converting between the r from a polar equation to the Cartesian x. You're always multiplying by cosine of theta. So there's cosine of theta. And there you go. Now to get the derivatives of this, we got to do we're going to take the derivative of the y and the derivative of the x. Please take a moment to do that. I'll do likewise. There's the dy d theta. The dx d theta, we've got to do the, hopefully you guys recognize this as the sine of theta squared. You use the power rule, and then the chain rule is where this cosine came from. This was 2 times the sine of theta to the first times cosine of theta. Now for the x derivative, we're going to have to use the product rule. We'll do the first, which is the sine of theta, times the derivative of the second, which is the negative sine of theta. So for the dx d theta, we're going to end up with a negative sine squared of theta. And then the second part of the product rule, is going to be this. It's going to be the second times the derivative of the first. Well, the second is the cosine. The first is the sine, and the derivative of the sine is the cosine. So we end up with plus the cosine squared of theta. And I'm just going to save some space and just, there we go. This is the derivative. Let me erase one thing. This is dy dx. All right. So from there, we already know where this thing is, don't we? No, we don't. In order to assemble a tangent line, we need two things. We need to know where this thing is at pi over 6, and then we need to know what its slope is at pi over 6. So let me do a little color switch here. We're looking at dy dx at theta equals pi over 6. Okay, those of you that know your unit circle, you're not going to have to draw this little triangle that I am always forced to make. Grounds me, I guess. Let's see, something like that. We've got 1, 2, root 3. There's pi over 6. Okay, so let's just start plugging in our values. And I end up with the slope of this thing is the square root of 3. And that's reasonable. I mean, as I look at this tangent line here, at least it's positive. I got that right. So there's root 3. I'll show you how you can get this slope value on your calculator. But let me erase a whole bunch of stuff here. Kind of tedious. What we have to do next is we have to get the x and y values. So to gather those things up, we have to gather up the thing that I just erased. Well, I erased it some time ago. Remember, y is equal to r sine theta, and x is equal to r cosine of theta. So our y, it's with green, it's a nice spring day. So we're looking for the y coordinate at pi over 6. Well, in order to get that, what we're going to have to do, r is the sine of theta. So we need the sine of pi over 6. And then don't forget, we're always tagging a factor of the sine of theta when we convert from polar to Cartesian. So our y component is going to have a sine of pi over 6 again. Our x component at pi over 6 is going to be, again, we're looking at the r, which the r is the sine of theta. There's a repeat of the r in each of the y and the x components. And then we've got the cosine of x tagged on as a factor of the x component. So the cosine of pi over 6. And I know I did it just a minute ago, but I don't remember them. So we're looking at 1, 2, root 3. So our y is going to be 1/2 times 1/2, which is 1/4. Our x is going to be the sine, which is 1/2, times the cosine, which is root 3 over 2. So we've got root 3 over 4. And we've now got the second ingredient for our tangent line. Our ordered pair is root 3 over 4, 1/4. All right, so some assembly required. If this were the AP test, I would not go for slope-intercept form. I would just point slope it. This would be y minus 1/4 equals square root of 3 x minus root 3 over 4. All right, I believe that's right. There you go. So that's an application of a derivative for a polar equation. Let me cut out of here and show you how you would get these components, at least on your calculator. If I wanted your calculator is not, let me see, can you do a, no, the best it'll give you is it'll give you the slope and it'll give you the value. So let's see the value. The value at pi over 6, there's your ordered pair. And then if you want and there's the position right there. If you want the slope at that particular point, I think you might have seen it. There it is, dy dx. So choose option 2. And the dy dx at, if we got to pick our, where do we want this slope? Well, we want pi divided by 6. And there's our slope. And I do know that 1.732, that is the square root of 3. So we got that right. Okay. Unfortunately, it doesn't give you the, I mean, you got to do the assembly to get yourself to a tangent line. All right. So we have graphed a polar. We have done an application of a derivative of a polar. I did talk to you guys about the important conversions that you need to go from polar to Cartesian. The last thing we need is to practice on integration. And let's find out, let's use calculus to get the area of this circle. I think we need this. Let's put our geometry heads on first. Let's figure out, you should be able to figure out what the answer, a geometry student should be able to figure out what the area of that circle is, right? So it shouldn't be any problem for you guys. So here's how a geometry student would do it. A geometry student would say, well, we've got a radius. Isn't that funny? I'm using radius, but that R is, well, maybe we need another letter for radius. Radius is equal to 1/2. We're looking for the area of a circle. Area equals pi r squared. Area equals pi 1/2 squared. Our geometry student would tell us that the area of that circle is pi over 4. Right? So let's get rid of this. I'm hearing the wind kicking up. We got to get out. We got to finish up. Enjoy ourselves a nice day. Area equals pi over 4. Let's see if we can if calculus is so adept at getting area. So let me erase more stuff. Oops, erase too much. There's a couple of hot buttons on this iPad that if you press them, things go terribly bad. That's why that all disappeared for a moment. I've kind of got used to it. I don't panic as much. Here's the general formula for integration. Area is equal to the integral from A to B of 1/2 r squared d theta. Okay, so if I wanted a wedge of this thing, suppose I just wanted a wedge of this thing. Suppose I wanted the portion from here to here. Well, this looks like we're at, this looks like pi over 4 here. And this looks like pi over 3. So this area right here, this wedge, it's got an integral to it. Well, where do we, the hardest part about doing polar integration is identifying where the bounds are. Well, we don't want to start at pi over 4. We want to start at pi equals 0. And what that's going to get us is it's going to get us, we've got all of these, basically the proof of this is you got a bunch of tiny little sectors, right? We're not making rectangles, we're not making discs or washers, we're making these little sectors. Okay, if I were to draw one better, it might look something like a really thin slice of pizza, okay? And hopefully you can appreciate this thickness of this slice is our d theta. And the radius, it comes from this radius. We can talk about why it's squared and then 1/2 in class. I just want you to experience having done one. But so where do we finish this integration? Well, we're clipping off all of these wedges or slices, and we're going to end at pi. We're going to pi equals pi, or I guess I should have wrote this a. Pi is not equal to 0. What am I writing? We're beginning at 0 and we're finishing at pi. That's what I wanted to write. So to set up this integral, and sort of reset some things here. Oh, I erased too much. All right, this is, this is r equals sine of theta. So our integral for this, our area of the entire circle, is going to be the integral from 0 to pi of 1/2 sine theta squared d theta. And you can do this on your calculator. I can tell you that in the ebook, they're going to ask you for an exact value, so your calculator's not going to cut it. In order to integrate a squared function, it's going to require a u substitution. And there are a couple of trig identities that you can write them down, but once you've done enough of these, you should have them memorized. Good, green as in good to go. You're going to need these. So the integration process would be as follows. We've got, this is equal to the integral from 0 to pi, 1/2. This should be cosine right here. That should be cosine of 2 theta. Apologies, cosine of 2 theta. So it's 1 plus or minus the cosine of 2 theta over 2. Get used to these. Forget about memorizing them. Just have a note card because you will need them a lot. All right. So we're looking at the integral of 1 minus cosine of 2 theta over 2 d theta. And this is squared. No, we did square. Never mind. Okay, I'm having a little. I think I'm being distracted by the nice weather outside. So we're looking at 0 to pi. I'm going to distribute this 1/2 through, so I've got 1/4 minus the cosine of 2 theta over 4 d theta. And that's going to be theta over 4 minus cosine of 2 theta over 8 evaluated from 0 to pi, I believe. All right, let's check that out. Gonna need a little space. So let's go up here. I actually did this on the calculator. I have not done this actual calculation manually yet, but let's analyze this, see what we get. Okay, so we've got pi over 4 minus cosine of 2 pi over 8 minus 0 over 4 minus cosine of 0 over 8. Oh my gosh, I think I got it. Okay, this is going to work. So when we evaluate this thing, give myself a little room, what we end up with is pi over 4. Cosine of 2 pi is 1, so we got minus 1/8 minus 0, and we're subtracting a negative, so this will be plus 1/8. And these guys cancel, and we do indeed end up with pi over 4. I think the geometry student is outside, playing in the garden and having a great time on this beautiful day, while us calculus students ground away to do something that was easy for the geometry student. But regardless, that is an example of how you would do an integration. Again, I don't. This little conversion of this trig identity is going to come into play throughout this particular section. I don't have it memorized because I don't use it that often. The only time I use that double angle or whatever type of identity that is, the only time I use it is when I'm integrating polars. So once a year for about a week I do this. So forgive me if I messed up the signs there or wasn't totally confident on the signs. Let's finish up by just confirming on the calculator how you would do this, right? So I'm going to get out of pen mode. My calculator is right there. Oh, I think Carmen got her other pig ear. All right, so let's get out of here. If you hear that crunching in the background, that is me, not me chewing on a bagel. It's my dog chewing on her pig ear. So anyway, we're going to use the math function. Go to integral, and we're going to go from 0 to pi. And our it's 1/2. I'm just going to put 0.5 in, that we don't have to mess with a fraction. And then you got to square the r. And remember, the r was the sine of theta. So I want to parenthesize, squeeze in a sine of theta, close off the theta, now close off the sine, and I got to square that thing. And then finally, I got to give a variable of integration, which is, it's going to default to theta. And when I hit enter, I get that, which if I, let's see, second pi divided by 4. Yeah, sure enough. Okay, so there you go. That's polars, and I'm supposed to be, what time do we close? We close at 1:10. I'm a little bit early, but I think I accomplished what I think we need to do. If you guys have any questions about the polars, or I'm sorry, the parametrics or vectors for this coming weekend, available. I don't need to be in pen mode, or I don't need to screen share. So I'm gonna come out of this. Okay. We're where we need to be as far as next week. We'll be doing just more examples. I think I'll show you the library of the other polar equations, and I'll also show you how to convert from polar into Cartesian. Again, I think about 2/3 of the ebook assignment is going to be about just converting the equations. There is one equation that you cannot do on your graphing calculator, and I'll show you that. And yeah, I don't have a workaround for that one. and we'll do a lot more example. I'm rambling here. You guys are good to go. You can hang on if you have any questions. Otherwise, have yourselves a great weekend. I'll see you next week. All right.